Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The revolutionary recasting of quantum electrodynamics accomplished through the spacetime approach, initially unveiled in Richard Feynman's 1947 paper, represents a pivotal moment in theoretical physics. This essay undertakes a detailed examination of the claims presented within that work, dissecting its argument and evaluating their internal coherence within the context of the physics it describes. We will proceed section by section, scrutinizing Feynman's novel formulations and their consequences to its understanding of the interactions between light and Section 1 Introduction of the Lagrangian formulation and path integral. Feynman begins the paper by asserting the equivalence of a path integral formalism to conventional quantum mechanics, a claim that marks a significant departure from the operator-based approach dominating the field at the time. He proposes that the probability amplitude for a particle to travel from point 1 to point 2 is found through the sum of complex exponentials, each weighted by the classical action evaluated along a possible path between the 2 points. This seemingly simple statement carries profound implications. The essential idea is that a particle, in the quantum realm, explores all possible trajectories between initial and final states, rather than adhering to a single classical path dictated by Newtonian mechanics. Feynman utilizes the concept of the Lagrangian, specifically the time integral of the difference between kinetic and potential energies along a given path, to construct the phase factor within the exponential. This reliance on the Lagrangian, rather than the Hamiltonian, proves crucial for extending the formalism to relativistic quantum field theory due to the Lagrangian's inherent Lorentz invariance. The assertion lies in the claim that this infinite sum over paths, when properly normalized, yields the same predictions as the Schrödinger equation, but with a completely different conceptual foundation. This is where the originality lies. It is simply an equivalent calculation. It's a genuinely new perspective. Evaluation reveals that the initial justification relies on arguments based on the principle of least action and the superposition principle, providing a heuristic foundation. The paper does not offer a rigorous mathematical proof of equivalence in this particular work. Such proofs would come later, developed through functional analysis and advanced techniques for handling infinity-dimensional path integrals. Section 2 Application to non-relativistic quantum mechanics. Following the introduction of the path integral, Feynman proceeds to demonstrate its utility within the more familiar realm of non-relativistic quantum mechanics. He applies the formalism to simple systems, such as a free particle and a particle in a potential, showing that the path integral leads to results consistent with the Schrödinger equation. A specific claim made is that by discretizing time and approximating the path integral as a product of ordinary integrals over intermediate positions for each time step, one can recover the time evolution operator. The time slicing procedure allows for a practical, though mathematically delicate, way to evaluate the integrals. His methodology involves a detailed mathematical manipulation of the path integral, demonstrating how the sum over paths can be approximated and evaluated in specific cases. He claims this method enables the calculation of propagators, which describe the probability amplitude for a particle to propagate from one point to another in a given time. The strength of this section lies in its concrete demonstration of how the path integral formalism can reproduce and often simplify standard quantum mechanical calculations. The mathematics, though not overwhelmingly complex, requires careful application of Gaussian integration techniques and a solid understanding of operator formalism. The utility of this section is that it provides a tangible connection between the abstract path integral and more familiar ground. Section 3 Relativistic generalization. The photon propagator. Having established the validity of the path integral in non-relativistic quantum mechanics, the paper undertakes the crucial step of generalizing it to the relativistic domain. focusing specifically on the propagation of photons. This requires addressing the issue of causality and incorporating the notion of virtual particles. A key claim is the formulation of the photon propagator, which describes the probability amplitude for a photon to propagate from one spacetime point to another. Feynman argues that, in contrast to classical electromagnetism, the quantum propagator allows for propagation both forward and backward in time, representing the emission and absorption of virtual photons. This is a radical departure from traditional thinking, suggesting that photons may travel both into the future. A pivotal component of this picture is the introduction of the Feynman propagator, which incorporates both positive and negative frequency solutions for the Klein-Gordon equation. The form of the propagator, as presented, directly addresses the issue of causality by ensuring that negative energy solutions are interpreted as particles traveling backward in time, effectively reversing the role of emission and absorption. This section represents a significant leap in conceptualization. The introduction of the Feynman propagator is deeply rooted in the relativistic covariance of the equations. However, it also introduces the uncomfortable, albeit necessary, concept of particles traveling backward in time, which needs careful interpretation to avoid paradox. Section 4, Electron propagation and the Dirac equation. The paper then shifts attention towards describing the propagation of electrons within the framework of the spacetime approach, incorporating the Dirac equation to properly account for the particle's spin and relativistic properties. This requires modifying the path integral to accommodate fermionic degrees of freedom. A specific assertion is the construction of the electron propagator, which, similarly to the photon propagator, allows for both forward and backward propagation in time corresponding to the emission and absorption of virtual electron-positron pairs. This is a critical step in developing a fully relativistic quantum electrodynamics. The methodology involves a generalization of the path integral to include Grassmann variables, which are anticommuting numbers used to represent fermionic fields. This incorporation of Grassmann variables is crucial for ensuring that the path integral respects the Pauli exclusion principle, a fundamental property of fermions. The electron probia, therefore, encapsulates the quantum-mechanical electrons while simultaneously accounting for the existence of their antiparticles. This section becomes mathematically intricate. The introduction of Grassmann variables requires a level of mathematical sophistication beyond that typically possessed by undergraduates. The physical implications, however, are profound, solidifying the notion of electron-positron pairs as fundamental aspects of the quantum vacuum. Section 5, Interaction of electrons and photons, vertices and Feynman diagrams. Having established propagators for both electrons and photons, Feynman proceeds to develop a perturbative theory for their interactions. This is where the iconic Feynman diagrams emerge as a visual representation of the different possible processes that can occur. A central claim lies in the assertion that any quantum electrodynamic process can be calculated by summing over all possible Feynman diagrams, each representing a specific sequence of particle interactions. Each diagram consists of lines representing electron and photon propagators, connected by vertices representing the emission or absorption of a photon by an electron. The methodology involves assigning specific mathematical amplitudes to each element of a Feynman diagram. Propagators correspond to mathematical functions derived from the Dirac and Maxwell equations, while vertices correspond to the fundamental coupling constant of quantum electrodynamics. The brilliance of the Feynman diagram approach lies in its ability to translate complex mathematical equations into intuitive pictorial representations. Each diagram represents a term in the perturbation series expansion of the scattering amplitude. By summing over all possible diagrams, one can, in principle, calculate the probability of any quantum electrodynamic process to arbitrary accuracy, limited only by the number of diagrams included in the calculation. The elegance of this approach made it instantly appealing to physicists. Section 6. Renormalization addressing infinities. A significant challenge in quantum electrodynamics is the appearance of infinities in calculations of physical quantities, such as the electron's mass and charge. Feynman addresses this issue through the process of renormalization, a technique for absorbing these infinities into redefinitions of the physical parameters of the theory. A central claim is that these infinities, though initially appearing to invalidate the theory, can be systematically removed by redefining the electron's mass and charge to match their experimentally observed values. This process involves introducing counterterms into the Lagrangian that cancel out the divergent terms arising from loop diagrams containing closed loops of virtual particles. The methodology involves identifying and isolating the divergent terms in the perturbative expansion of physical quantities. These divergences typically arise from integrating over all possible momenta of virtual particles in loop diagrams. The counterterms are then chosen in such a way that they precisely cancel these divergences, leaving behind finite and physically meaningful results. This section represents one of the most mathematically and conceptually challenging aspects of the paper. The process of renormalization is not merely a mathematical trick, it reflects a deep understanding of the relationship between bare parameters, those appearing in the Lagrangian, and physical parameters, those that are actually measured in experiments. The success of renormalization in quantum electrodynamics provided strong evidence for the consistency and validity of the theory, even in the face of apparent divergences. Section 7 Lamb shift and anomalous magnetic moment. The paper then delves into two specific applications of the spacetime approach: the calculation of the Lamb shift and the anomalous magnetic moment of the electron. The Lamb shift refers to a small energy difference between two energy levels in the hydrogen atom, while the anomalous magnetic moment refers to a deviation of the electron's magnetic moment from its value predicted by the Dirac equation. A central claim is that the spacetime approach, combined with a renormalization procedure, provides accurate theoretical predictions for both the Lamb shift and the anomalous magnetic moment, in excellent agreement with experimental measurements. These calculations provided compelling evidence for the power and accuracy of quantum electrodynamics. The methodology involves calculating specific Feynman diagrams that contribute to the Lamb shift and the anomalous magnetic moment. These calculations are technically complex and require careful evaluation of loop integrals. The results are then renormalized to remove any remaining divergences, yielding finite and physically meaningful predictions. The agreement between theory and experiment for these two quantities is remarkable. It demonstrates the accuracy of quantum electrodynamics to an unprecedented level of precision. The Lamb shift and anomalous magnetic moment calculations are considered cornerstones of the theory and provide strong support for the validity of the spacetime approach. Section 8 Comparison with other formalisms and advantages. Feynman explicitly contrasts the spacetime approach with a more conventional operator-based approach to quantum electrodynamics, highlighting its advantages in terms of conceptual clarity and computational efficiency. A key claim is that the spacetime approach offers a more intuitive and physically transparent picture of quantum processes, particularly in the relativistic domain. The path integral formulation allows for a direct visualization of particle propagation in terms of sums over trajectories, avoiding the often abstract mathematical formalism of operators and commutation relations. Furthermore, Feynman argues that the spacetime approach is computationally more efficient for calculating complex quantum electrodynamic processes. The Feynman diagram technique provides a systematic way to organize and evaluate the different terms in the perturbation series, streamlining the calculation process. While the operator-based approach is mathematically rigorous and provides a solid foundation for quantum field theory, the spacetime approach offers a complementary perspective that emphasizes physical intuition and computational practicality. Section 9 Limitations and open questions. While celebrating the successes of the spacetime approach, Feynman acknowledges its limitations and identifies open questions that remain to be addressed. He explicitly recognizes that the perturbative nature of the theory limits its applicability to strong coupling regimes, where the interaction between particles is very strong. A specific limitation lies in the convergence of the perturbation series. While the calculations of the Lamb shift and anomalous magnetic moment are remarkably accurate, the perturbation series expansion is not guaranteed to converge in all cases. In some situations, higher order diagrams may contribute significantly to the final result, requiring a more sophisticated approach to calculations. Furthermore, Feynman acknowledges that the spacetime approach does not provide a complete solution to the problem of quantum gravity. While it offers insights into the quantum nature of interactions, it does not address the fundamental issues of quantizing spacetime itself. This section demonstrates Feynman's intellectual honesty. He is willing to acknowledge the limitations of his own work, paving the way for future research and development in theoretical physics. Section 10 Reception and subsequent developments. The initial reception of Feynman's spacetime approach was mixed. While some physicists immediately recognized its potential, others remained skeptical, particularly those deeply invested in the traditional operator-based formalism. The visual elegance of Feynman diagrams and the computational ease they offered gradually won over the community. Significant subsequent developments include the generalization of the path integral to other quantum field theories, such as quantum cryptodynamics, the theory of strong interactions. The Feynman diagram technique has become an indispensable tool for particle physicists, allowing them to calculate scattering amplitudes and predict the outcomes of experiments at accelerators. The development of non-perturbative techniques, such as lattice gauge theory, has also helped to address the limitations of the perturbative approach, allowing physicists to study quantum field theories in strong coupling regimes. However, perturbation theory continues to be a vital tool for theorists. The enduring impact of Feynman's spacetime approach is undeniable. It has revolutionized our understanding of quantum electrodynamics, thus providing a framework for developing and testing other quantum field. Conclusion. Richard Feynman's 1947 paper on the spacetime approach to quantum electrodynamics constitutes a watershed moment in the history of theoretical physics. Its claims, centered on the path integral formulation, the Feynman propagator, and the diagrammatic representation of particle interactions, offered a new and powerful perspective on the fundamental laws of nature. While the paper is not without its limitations, and the mathematical framework presented in the paper would be further formalized and refined over time, its impact on the field is profound. The enduring legacy of the work lies not only in its technical achievements but also in its ability to provide a clear and intuitive picture of quantum processes, inspiring generations of physicists to explore the mysteries of the universe. The revolution Feynman initiated continues to shape the landscape of modern physics.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.